Hi folks, so we're back to do some more programming with differential data flow. And what I thought we'd do today, I've set up a project, but let me talk you through what the goal is. What I thought we'd do today is follow a path that I sort of stumbled upon this morning. Reading on the Hacker News, there was this post. Sorry, I guess the post is actually from maybe a week ago. When parallel pull don't push, and I'll talk you through what that is. But there's lots of people talking on Hacker News about it. Um, the idea in the post, which is not a bad idea, is that often in parallel programming, when you have the choice of writing a program that repeatedly sort of has different communicating actors in it, it can make a lot of sense to pull information from actors, from your neighbors, for example, to update your state, rather than pushing changes at your neighbors. And that's not wrong. Sometimes this does make lots of sense. And the main motivating reason is that when you have people pulling, you have a bunch of reads going on in parallel, essentially. So a bunch of people are reading from each other's locations, and each of them are going to do a single write to their location. So you conflict on reads, but then there's no conflicts on writes. And that's a lot more pleasant generally than the other way around, the push model, where there's a single person who reads some state and tries to update other people's states, and there's a lot of conflicts, and you have to be a little careful. And generally, the former is going to perform better if you're planning on doing the same set of reads and writes. Better to do them using pull than by push, though probably there's a reason to make the opposite argument, and we're not going to go too deep on that. What I thought was interesting, though, is that the problem, particularly the first problem that they looked at a few, but I hadn't heard of before, and it turned out to be sort of cute. But it's this Abelian Sandpile model right here, and there's a link to it over here. There's a Wikipedia page about it. I'll try to put a link in the video. But the general gist is that what you have is, I'm just going to oversimplify, I'm sure it's super complicated. But you have a grid, and the grid, each of the grid cells has some number of grains of sand on it. Those numbers are like 0, 1, 2, 3, 4, 5, 6, some integer number of grains of sand. And any cell that has 4 or more grains of sand spills. So it should take 4 of those grains of sand from its pile and add 1 grain of sand to each of its immediate neighbors. And that process, you can run that process indefinitely and see what happens. There's some interesting bits of math around it, though. The reason that they're called Abelian sandpiles is that it doesn't much matter what order you run these things in. So any pile that has 4 or more grains of sand in it, if it moves those 4 grains out to its neighbors, it doesn't matter if you do some other neighbors first, but that's going to happen no matter what. The grains moving and where they go is a done deal at this point, and it doesn't really matter if we run them all, let's say like one at a time in sequence, or if we do them all in parallel, which is great. We like doing things in parallel. So I thought what we might do is try and implement this sort of rig. Generally too, this picture doesn't make it super. There's a video here. It's not. I'll play it while we're talking. The black in this, I believe, are the highly stacked locations, and what's sort of happening over time is the highly stacked locations are spilling outwards. The very edge of the rectangle is sort of like the edge of a table or something like that. So sand that reaches it will spill off and just fall off onto the floor or below or whatever. So with time, what happens is that the dense regions, which you can see sort of have on average more than 4 things in them. 4 or more things in them, are going to need to spill outwards. Like they're not stable in that space. But the spilling takes some time, and you can sort of see pretty interesting patterns show up as you do all of this spilling. You can also sort of see, if you watch a little bit, that not everything's changing every single iteration, and that's maybe one of the interesting places that differential data flow comes in. We're going to try to see if we can maybe write this dynamic process in the framework of differential data flow and try to see how long it takes. We're not my personal goal is not to try to argue that this is going to clobber any carefully hand optimized parallel program. But that by writing it in this interesting Dataflow framework, we can do some cute things that it's a little tricky for the more the lower level implementations that just talk about doing a bunch of lookups in various locations. In fact, we're going to try to go faster in the end, but we're not going to start out there. We're going to start out just writing simple let's emulate this process sorts of algorithms. So let's start with that. So I put together a very empty project over here, and we're going to need to start from scratch. I'm going to need to remember how to create these projects. I believe we need to remember how to type. We're going to need a timely dependency. We're going to need a differential data flow dependency. Both of these are on crates IO, so we just need to throw in something like this, I hope. Let's see what happens over here if we do a cargo check. Okay, we wait, apparently. Yeah, we seem to wait quite a while. Yeah, internet seems to be live, so it's a mystery what. Yeah, it's live. Oh, no. Oh, that's a disaster. All right, some amount of internet failure later. We are pulling down all the necessary crates. I suppose the video would have been a bit more pleasant if I had pre-done this for you and you don't have to watch. But it's helpful for me to start over from scratch various times so that I remember how to build these things. Good. Okay, so we've pulled in all of our dependencies. We haven't actually done anything yet, so it's not super surprising that it builds. We have a pretty boring little function here. I'm going to do what I normally do, which is steal some existing code from a prior project, which will make this a little easier to get up and running without me guessing about what I should be typing. So this is the Sudoku example from a little while ago. We will just pull in some little bits of boilerplate. Our main function is going to need to create a new timely data flow context. We're definitely not going to print out hello world anymore. We're not going to run BFS, we're going to run a Sandpile. That's good news. And we're going to want to almost certainly put together a little bit of data flow that looks like so. I'm going to copy paste these folks. I think this is all we're going to need. So let me close off some of these things before we try to do anything too exciting. So we have just gone and created a new timely data flow scope, computational scope up here. This will spin up some workers, read any arguments we've provided to the input about number of workers to use, and start each worker running this bit of logic in here, this closure. And what we're going to tell the computation to do is sort of cribbing from the previous version. Let's get ourselves a probe. This is a way that we can measure progress in timely data flow. And let's build a new data flow, so a new little bit of computation within each of the workers that is going to create a new input. We call it start, and nothing else happens yet. So we need to write some computation from this point going forward. And down here, let's say we will want to load up the inputs with initial Sandpile state. And we'll talk about what that means in a bit. The blog post computes a specific thing in the Sandpile model that it tries to find this identity configuration, like sand that you can drop down that will shake around for a little while, but eventually return to the original state, which is sort of cool. But there are a bunch of things that we could do that could be interesting here. So what we're going to do instead, though, is try to describe this Sandpile model. And what I mean by that is let's actually make some notes about the type of data we're gonna represent and what we might want to do with it. So I'm just going to type a little bit here and sort of. So in the Sandpile model, we have grains of sand on some sort of large grid. We could talk about an infinite grid in principle, though in practice what people do is sort of an n by n ish grid where sand falls off the end. So so each grid cell with 4 or more grains of sand on it will spill by which I mean will remove 4 of its grains and add 1 to each of its neighbor grid cells. So some weird things can happen. Like if you have a stack 4 high, it can give 1 grain of sand to each of its neighbors and go down to 0, which isn't what you'd think would actually happen in a pile of sand, but that's okay. That's just what the rules are. Now, fortunately, all of this is Abelian or commutative in the sense that it doesn't really matter what order we apply all these rules. It doesn't matter in the sense that we reach the same conclusion. And this is pretty reassuring. It means we don't have to think too hard. We just need to start applying the rules, and if we reach a fixed point, we will be delighted. So I thought we might just try writing that out. We start from the start pile, and we call our handy-dandy iterate method, which takes some inner iterate, basically, some Sandpile state. So we start from a Sandpile state of start, and then we iteratively take that state and do some stuff to it. So we're going to need to write a little bit of a program now, a data parallel program in differential Dataflow that takes inner and thinks a little bit about what should happen. What should the state of the Sandpile be next? And my sense is what we want to do is okay. Sorry, I haven't even said what start should be. So my thinking is that we are going to start from and maintain a collection of, I'm thinking XY pairs, where the multiplicity at each location is just going to be the number of grains of sand. So great. So this is the sort of thing that strikes me as reasonable. We could do things differently. We could have a triple X, Y, and a count, but it turns out that differential Dataflow is already tracking the count for us because it handles multi-sets. So I think this is pretty reasonable. And what we're going to need to do is, if someone shows up with a description of these collections, a bunch of XY pairs indicating how many values there are, or how many grains of sand there are at each location, we need to figure out, well, one iteration from now, what should that look like? So my intuition is that we're going to want to count things. So we might want to do inner.count. This is going to produce pairs of x, y, and a number. And informally, we're going to want to do two different things here. So let's, I think we can just write this as sort of a complicated flat map. Maybe, I mean, we'll see. So the flat map takes as input a pair of a row and a call. There's like an x and a y and a count. And we're going to want to think through what goes on here. So flat map is just an operator that says for every record that comes in, I get to produce a sequence of outgoing records. A sequence in the sense of, the order doesn't really matter, but multiple. Well, it's an iterator over output values. Could be empty. We produce nothing. It could be a singleton. So for example, we're going to write this in a bit of a grotty way, actually. So we're going to we're going to create a new output vector. Sorry, not met. Cool. We're going to create this output vector, and we're going to populate it. Sorry, I'm just getting wound up by the indenting here. Let me fix that. And the idea is that based on the value of count, we're going to do a few different things. So we're going to retain some amount of output here, and we are going to actually fascinating. Sorry, I'm just we might need to use a different operator. So what we're supposed to do is produce various outputs for each of these row call count things. And to be honest, what we'd like to avoid doing is if count is 1,000,000, you don't actually have to produce 1,000,000 different outputs. We'd like to be able to directly indicate that 250,000 grains of sand should go to each of these other locations. So I think what we actually are going to want to do, let's see, it's the right way to do this. So I'm tempted to say what we actually want to do. There's this explode operator. Oh, this is fascinating. Okay, sorry, I actually don't know the right way to do this off the top of my head. So our choices are, we have, we could write a reduce. Like that's, okay, this is probably the easiest way to do it. Just write a reduce, because then we can write whatever bits of logic we want. Just to talk through the other options, having counted everything here, and counting is sort of nice, it's simple. And the flat map operator lets us look at the count and do whatever we want, but we actually have to dump out actual records and not manually drive the counts around. We could use the explode operator, which lets us look at the data. And maybe explode works fine here. We look at this data and we're allowed to produce both pairs of data and count. So it's a way to take data. It's sort of the inverse operator to count in some sense. So maybe that's actually right. Maybe we can pull this off. So explode takes some data, and we're meant to produce an iterator over pairs of data and count. So let's see if this works out. So what we're going to want to do, I believe, is take a peek at count. And one way to do this is that if count is 4 or greater, we should subtract 4 from it and add 1 to each of these other locations. We could try to be very clever, though, if we want, and say, let shed be count over 4. And this is going to be 0 up until 4, and it's basically the integer multiples of 4 contained in count. And we should, I think, just be able to do output dot push. So what are we going to be pushing? We're going to push a pair of, well, for sure the current row and column with a multiplicity that is count minus 4 times shed. So these are the number of elements that are left behind. Essentially, it's count modulo 4, but yeah, so we shaved off a bunch of elements here, and now for each of the other locations, and probably I'll just do these by hand actually. We'll do, rather than some weird loop, output.push. Comma call, that we're gonna need to add one, subtract one, that sort of thing. So if we add one and add one, let's just make 4 copies of this, and then we can do each of the appropriate changes here. So so what we're doing here, hopefully, is preserving the total number of records, the total count, by, sorry, we haven't actually produced the results yet. Output. So we've gone and we've counted for each cell location, row count, the number of grains that are present there. And now we've reflected on each of those counts and said, hey, you know what? Let's think about shedding in each direction this many grains of sand. And we're going to obviously remove those here. We're now producing pairs of data and intended counts. And we're going to, do what we think is the right thing, which is to dump these in various different directions. And then produce our output. And before we do any more, actually I think we'll see if this runs. There are some rules about making the sand fall off the edge, but in principle, actually, we haven't put any data in yet, so we don't even need to worry about that. But let's check this. Oh yeah, sorry, not unwrap, but expect. The time of the computation returns something which is you must look at it, and it just reports whether we failed or not. All right, so good point. So we haven't. We've left some things underspecified because we haven't actually used them. So let's do a see that sort of thing. So this is, no, I'm sorry. Oh, that's terribly wrong. We want to put that after the iteration. So this will iterate this movement of grains of sand around. We have from each inner gone and said, you know what, we should move the sand around in the following rule, go back around again, keep repeating until we're done, and the probe at the end of the iterative process tells us, well, how many of these processes are completed, which ones are still in play, that sort of thing. All right, we haven't actually used the input collection yet, so it's still a bit mystified about what type of semi-group, apparently. Yeah, good point. So we're planning on using integers. We're gonna these counts are going to be integers, but we haven't actually told anyone that yet, so it's still a bit confused. But let's put some initial data in here. So let's imagine that I guess we can do it down here. So we're gonna have some grid size, and let's let this be std. Is it n args? That's how you get an integer out of the command line there. Let's let these be, I'm going to say iSize. iSize is a weird thing to use. Do I32 just do I64 because we're big data people. And yeah, okay, so now that we have this grid size, what we're going to do is for x in, should we start at 0? Let's start at 0. Grid size for y in, actually we don't even need to do this. We can just dump a pile of stuff in. We don't even need grid size yet. Sorry, we're totally getting ahead of. I'm thinking already about what we want to do for the blog post. But let's just start with something more simple. Let's start with putting a whole bunch of stuff at 0, 0. So let's do start dot insert. We need to do insert. Lets us insert one record at a time. We actually want to put like 1,000,000 in there or something like that, just to make it interesting. So start dot, is it update? Let's see if that actually works. And then we're going to do I propose 0, 0, and we should figure out in differential data flow what an input takes. So there's insert and remove. That's great for an input session. There's also update. Great, that's what I'm looking for right here. Update takes an element and a change. So we'll do that. And let's do maybe and let's run for a little while. So while probe dot less than start the time worker dot step. This is a standard timely data flow idiom, though we've screwed up a little bit in that we want to do a start dot advance start dot advance 2. We're gonna just go to round 1. We start at 0. We start at whatever, for the timestamp type, whatever the minimal element is. And we're going to need to call flush also, just to make sure that timely data flow can see that. Great, so let's check this. There's a lot of crazy stuff going on here. No method, update found for type, empty thing. All right, we need to do more than that. We need to actually return the start. Is it handle? Start input. Cool. We actually need to return it out of the data flow thing to actually bind it up here. We previously just had a semicolon at the end, which is upsetting to programs. Cannot multiply I size to I32. Well, that's a good point. So what's the problem here is that I think that we have a few different types going on in here. So in particular, we're coming out, and when we produce a result here with a count on the outside, it needs to be multipliable by the type that we're using for, so we just need to pick a consistent type, both for counts. Yeah, I wonder why this is quite so mysterious. Let's try an I64 here. And I'll have to figure out why it's imagining it wants an I size. Maybe we're just trying an I size. This is Rust being very particular, which is that's probably a good thing about. Yeah, okay, so that worked. I'll need to track this down, but it got in its head that something else around here is an I size, not the type of integer that came in, and. Yeah, probably, no, wait, I'm not sure. I was thinking count, so count should come back with whatever type we use to count the things in iter, which I thought was going to be, I32s or whatever, but this is some annoying type inference issue to track down. We're just not going to bother. Things build. We have, we have some little minor annoyances in terms of like unused imports, but let's think about running this. I guess we'll just cargo run it and see what happens. I mean, what we expect to have happen probably is that these million grains of sand, which might be too many, are going to spill outwards from the 0, 0 point. And we haven't put any boundaries into the sand pile yet, so they're just going to keep spilling. I mean, they're going to oh, great! We can see which these things are to delete now. Time data flow. We don't need differential data flow collections. We don't need differential data flow lattice. Sweet. So it's running, and what I should do actually is make this be a command line argument. just so we can check and see if this is also running in the debug mode, so like we're not super worried about how long it takes at the moment. So it should happen. I mean, it might not. We might have written something sketchy. Oh no, it finished. Oh. So what's supposed to happen is it's supposed to smear the grains of sand around. One thing that we could do to try to see if that's the case is to take the results of start to iterate, or maybe just before we probe it. What we have now are a bunch of XY values with various counts. We could extract those counts and then discard the XY part. Like if we don't really care about the whole, which row and column do you belong to? And we just want to get a sense for what is the distribution of count. What is the distribution of number of cells with different grains of sand on them? So how many of them have 4 grains of sand? Oh, hopefully none, but how many of them have 0, 1, 2, 3? So we're just going to peek at that. So grains, let's say, and count. Yeah, I'm not sure what to say here. I guess we didn't need to split these apart as a pair, but let's. So this might do a thing now. Let's see. Okay, it's warning us that this is irrelevant, which is true. And it's gonna run a while. And tell us down here at the bottom now. Let's see if I can send higher up. That 1 occurs 112 times, 2 occurs 156 times, 3 occurs 192 times. We're not actually able at the moment to visualize where these things are, but they have no particular bounds on how far they've smeared outwards. I'm a little curious to know how many times they've done that though. So actually, what I'm going to do is steal this and put it inside a loop. Where do I want to put it? I'm going to put it just before the count. Yeah. If we put it just after the explode, unfortunately, we see it before it's been consolidated down. I think we'll still see it before it's consolidated down, which is a bit annoying. Yeah, this is annoying. Sorry. It's just we're in a world at the moment where everything still has all the rows and columns attached, and we could pull out this information for sure, but it's a bit annoying. I mean, it lives right here, kind of. We could steal that and add some printy prints. Yeah, let's do it. Let's figure out how to make this. So we've got our counts. We are eventually going to do counts.explode, but before we do, let's do this nonsense here again. And I'll put a like a tab in here or something like that so that we can visually distinguish things. And I'm gonna, because I can, do a really spilled of this. Just start to see how long this takes. We don't really have a very complicated data flow here. Actually, it's a lot simpler than I thought it was going to be. Like if it's just a count followed by this explode thingy. But really spilled will still take 20 or 30 seconds. 20 or 30 seconds after it gets through building all of these dependencies. Oh, wait, hold on. Okay, sorry. First, we actually have to write proper code and stuff like that. We need now, well, curly braces, because we've written a bunch of stuff, which is a totally fair point. And do I like how that's indented? I don't care at the moment. All right, that looks more syntactically correct, at least. Just as a side comment, this bit of logic we've added in to monitor things here is actually pretty cheap, turns out. So since we computed the counts anyhow, this is potentially expensive. All right. So we didn't have this on the critical path of data processing, so it sort of took a little while for it to figure everything out. But you can see now that we have some 160-ish iterations that went on to spill all of that stuff outwards. In principle, we could walk through what's going on here, though it's not strictly necessary. We start with everything in one location. So I feel like we have this in backwards, but maybe I'm wrong. Sorry. The number 1000, there's one location that has height 1000. Then in the next step, there are 4 locations that have height 250. And as things go on from there, I guess things get a little surprising. There's 4 locations with height 2. I guess there's just some interactions in the corners, for example, and stuff like that, where actually I have no idea. I'll not pretend to be able to figure out what this looks like without actually drawing a picture. Ideally, though, it all makes sense. Height 2, yeah, possible. We could actually unpick that and see what it is, but I'm gonna sort of trust for the moment that this is not wildly incorrect, or to not at all incorrect. But let's make one little change. Actually, sorry, I'm gonna run this again with some timing information on, just to see how long it takes. All right, didn't take very long. And if I make it a little bit bigger, let's see. So I think a thing that's happening, and we'll have to double check, but I think a thing we're gonna find happens is that it slows down. I made it large enough that it doesn't just finish quite quickly. And what we'll want to do, so the reason is we're doing this iterative computation, but we're doing it in a context where the input here, start, has been advanced to time 1, but it hasn't been closed. So we're doing all this work shuffling sand around, and we're leaving enough notes behind so if someone comes by and adds 1 more grain of sand, we can update all of these rules relatively easily. Though, as you can see, it's taking us a while to get there in the first place. So let me stop this and see if it behaves any differently. So we got like 1,000 iterations done in almost a minute. Let's see if it behaves any differently if instead of these 2 lines, if I remember how to comment stuff out on this. No. I have a bunch of fun layers on my computer, and I haven't quite gotten the muscle memory down to remember exactly what the shortcutting is for commenting stuff out. So instead of doing this, let's do start.close. And I don't believe we need to flush it if we do that. Which is good actually, because close destroys the reference, or consumes the reference. To close, we'll have to comment this stuff out as well. We can't keep looking at the time inside start because we closed it. So that's fine. Timely data flow computations run to completion at the before they return, so they finish out whatever computation they've got done. So we'll end up doing all of this work as part of closing out the computation. We should still see everything just flow on by. But I'm hopeful it'll be faster. In particular, yeah, I think we're going to hit 1,000 pretty quickly here, yeah. Cool. So that was much faster. Actually, I think that also included the time to build the code. Let's try that again just to make sure. So the 30-second reading was not, I don't think, a faithful representation of things. So we're grinding along, printing stuff out, and yeah. So 13-ish seconds to do these 1,000 iterations, where there's a lot of different things. So this is all iteration 990. All iteration 990. Oh my goodness. A lot of stuff going on there. So we're seeing that, we have grain heights of 1 up through 65 or so. And it's going to take a little while for this to sort itself out. One of the things you could sort of see from the video over here, if we get back to playing it, is that there are these little ripples of action that sort of topple. Think of maybe more as like little sand dunes or something like that. They spill onto the next one, and that causes them to spill and sort of keeps going in this sort of interesting cascade. So we have however many it was our 10,000, 100,000 sand grains spilling around in various directions. One of the things that we do in this blog post, they do in this blog post, is imagine that they're on some finite surface, so there's sort of bounds in each direction, and we're going to drop things onto the floor if they fall off of the edge of the grid. So what I'm going to do is just grab another argument here, 2. And actually, we're going to need this a little higher because this is going to be part of our data flow. It's not just going to drive our initial input. We're going to want it, let's say, right here. And the gist is going to be that each time around this loop, we don't just shuffle the grains of sand around, but if anyone has sort of fallen off the edge of the grid, we need to worry about that. So if we might put it basically just like a filter in here that says if you are row or column with the property that I'm not sure what way to do this. We could do like row.abs greater than grid size. Sorry, this is the requirement to keep things. So let's do it less than grid size, which, yes, I understand isn't exactly the complement. So let's check out and see if this builds. Rows and columns were, I just said 0 down there. Hopefully it's going to figure out that they're eye sizes. Yeah. All right. Well, it very much wants to know some explicit sizes here, so let's make sure that it knows that these are eye size and eye size. One of the annoying things about type inference in these programming languages is it can't always tell you what it didn't understand. So it's like, yeah, well, I couldn't figure out a type. Why could you figure it out before the filter, right? And presumably it has something to do with the fact that we're comparing various things now to eye sizes, and it can't find. It's a total mystery. Like, let's check and see if this still works as advertised. Yeah, well, that's great. It makes total sense. This program. This program, though, is madness. So let's I don't actually know what abs does, so maybe that's part of the problem. Let's find ourselves a oh yeah, 5 years, 5 months ago. That's not a very good call for us. Let's write this just a bit more explicitly, and we cannot. I mean, it's possible that abs is returning floating point values or something mental like that. So we're gonna try to pick row less than. Oh my gosh, this is gonna be a disaster, right? Isn't it? So obviously, okay, the right way to do this. Everyone knows how to do these things. Great. We're gonna totally. See if this works. This is a very bad idea. Don't do that. Argument requires that grid size is borrowed for a static. Does it just tell us that we want to do a move in here? That's super easy if that's the case. A little weird that I didn't figure that out before, but. All right, this should crash because we didn't supply a grid size as an argument, but we'll at least get it compiled. And I don't know. What's this going to be? 199 by 199. Let's do that. Can't actually tell if this is qualitatively different. Actually, let's make sure it's qualitatively different. Let's do 10 by 10 or 19 by 19. Cool. So that finished incredibly quickly because. Wow, super quickly actually. Like that got up anyhow. Because as the grains move towards the edge, they fall off. So although we started with 100,000 grains of sand, only 3 times whatever it is, 19 squared. I'm not proud of how we're using grid size here. 3 times 19 squared total grains of sand actually fit on the board. And that's something that's a bit like 1200, I think. So the sand just vanishes at some point, and since it's vanished, it doesn't cause us any fun iteration problems. Like we're not constantly trying to figure out where it needs to go. Just whoosh, some of it's gone. Some of it will be left behind. We can see that at the end. Absolutely, there were this many piles of heights 1, 2, and 3. And you can see that definitely doesn't add up to 100,000 anymore. So a lot of the grain just gone. Grains of sand, sorry. This is all sand, not grain. So you can sort of see that this process, like having a boundary or not, and we can clearly effectively get rid of the boundary by just making the number massive. It's unlikely that the grains of sand will actually spill this far. I think what mathematicians are working with these things to try to study potentially are you get some math that's the constraints on the shapes that can come out of this. If you have a single massive pile in the middle, as it spills, it's going to spill any movement that happens in the left-right direction also sends some movement into the up-down direction. So things can't spill massively horizontal without doing some vertical spill, and that's you start to populate an area now, and you just can't do all that much of it. I'm not sure why we're running this. So just to get us to like a place where we can pause for a moment, we're gonna need to fix up this grid size thing. I'm sorry. We'll do it later. The starting everything out at some particular singular pile is fine, but it's not what actually goes on in the blog post. So what the blog post does is populates each of the grid cell locations with some small fixed amount. In particular, they're trying to solve this problem that is a configuration of grains of sand that you can drop onto an existing puzzle or whatever, existing sand piles that once it wobbles around for a while will settle down in its original state again. So the sand you dropped on will probably end up falling off, like not those actual grains, but they will replace any other sand that falls off. And the goal is to find, if you think of the function f as describing this iterative process, you want to find some, what's the right way to say it, I guess? I think it's roughly this, that you want to find some y, so that if you iterate the process on the input, you arrive at some stable configuration. And if you iterate the process, let me just write it slightly differently just to risk being less wrong. If you iterate the process to a stable point and then add these grains of sand and get back to iterating it again, you come back to the place that you got to initially. And I suppose this only needs to be true for stable configurations, clearly. If you're in an unstable configuration, you put some stuff on top, you're not going to end up back in a unstable configuration. You don't end up in unstable configurations. And apparently the way to do this, there's several ways I expect to do this, but one way to do this is to iterate the process on some configuration, which is starting from all sixes minus function applied to starting from all sixes. So if you put sixes on each of the locations and you spin that to completion, figure out what that is. Notice that, like in any stable state, all of the counts will be at most 3. So if we then take our sixes, subtract those things up through 3, and drop them on top of all the grains of sand, this is meant to be an example of such a y. And you can sort of see why it might be stable. I mean, I'll let you do this on your own time, but because of this Abelian property of the sand movie aroundy stuff, there's some sort of distributive properties essentially over, if you want to think of this as, we could go and do the iteration for all of this 6s stuff first, kinda, not exactly, but kinda, and then it plausibly ends up effectively canceling out with this stuff left behind. Now, that's not right, because, or maybe it's right. I don't want to pretend that that's right. Like, it might, the number 6 is possibly chosen so that these things, even at their highest height, won't impede movement of these grains of sand, but like, this is probably a reasonably non-trivial thing to think about. I haven't thought about it at all. Just cribbed it from the web pages that we saw earlier. But what we might look into studying is, like, how long does this take? And potentially, if we've done that, how long does this take? So we could think about populating a start initially with all of these sorts of bits of data. So let's do that. Let's do this is not the correct bounds to use, but I'm super lazy at the moment. And we'll see what happens. I guess what we could have done, if we put the filter early on, we would make sure that, it's a little, I mean, we do want to have this filter somewhere in various places. The problem is, like, we're sort of off by 1 here. We're going to have an entry at negative grid size where we shouldn't, because this is a strict inequality. We could just copy this filter and throw it up here, for example. Anyhow, let's see what happens if we do this. So the first argument just gets ignored. Oops. Grid size is in the. Okay, we'll make another copy of it because we can. I32s, huh? Okay, right, yeah. Rust, again, being super helpful. So I guess part of the problem is that Rust type inference says if you have an unadorned integer, let's make that by default an I32. And there's clearly some reasoning that could have possibly led it to determine that as a good choice, but it's pretty circuitous, the path to realize that there is no implementation for any type other than isize. So we're running this thing. What are we running it on? Sorry, I didn't actually notice. Size 100 thing. That's fine. We're totally ignoring, I think we're ignoring pile size. Is that right? Yeah. Let's do it on just 10 so that we don't. Okay. So that was quite brisk. That's great. And it took almost 100 rounds, which is sort of cool, actually. Or I think it's potentially interesting. Like you might have imagined, or you can do some quick math and say, this is going to have to take, for board of size n, it's going to need to take order n-ish rounds at least, because the grains of sand in the center need to make it outward to the boundary. And that just has to happen. That doesn't happen any faster than one movement, right, left, up, down, each round. What we're actually seeing, though, is that it seems to take maybe, I'm just making this up, but like maybe more like quadratic amount of time. Let's try it with just a little bit more. This is all totally new to me, by the way, so I'm just sort of seeing this with you for the first time. Might be looking a little bit like 400. Again, just making that up. Not sure we want to stick around for this whole thing. So if we're right, then that should go to 10,000-ish, which is going to take longer than we actually want to watch. But I'm sort of curious to see, and it's getting slower because we're making the board bigger at the same time. I'm sort of curious to see what sorts of changes are going on though. So if we just look at, here's one round, for example, of changes. All of our heights, all of our heights are 1 up to 7. That makes sense. There are no 0 height things because 0 is just absent data. Those cells exist, but we just don't write down any data about cells with no grains of sand on them. And things are going to be at most 7, and you can sort of work that out if you want. But like at the beginning of a round, things are supposed to be, well, imagine that in a round, if you're 4 or greater, you're going to go all the way down to 3, and you're going to get incremented by at most 4 if everyone else is in a similar state. So having started with sufficiently small counts, like 6 everywhere, there's just no opportunity for anyone to accumulate to a very high height because they can only ever increase by, well, if their neighbors are not tall, by 4, 1 from each neighbor. So as long as this invariant gets maintained, the person's only going to, if they're at most 7, drop by at most 1, so they're going to contribute at most 1 grain to their neighbors. They're going to gain at most 1 grain from the neighbors, so they're never going to get very high. So we're mostly just shuttling data around between 1, 2, 3, 4, 5, 6, and 7. And this will continue for a while, and the number of iterations might be quadratic. The amount of work to do is also quadratic, so this might be like, sort of this grid size to the 4th type thing going on in terms of total time. Let's see if we'll pick something slightly smaller. So we're thinking maybe 900-ish. Yeah. 3 seconds. I'm going to kill the inner printouts, even though they're super interesting. And we're just going to look at a few more of these things and then probably take a little bit of a break. There's more cool things to do with this in particular. One of the things I'm going to try to come back to and hopefully make a point about, though I haven't tried doing this ahead of time, so I might just end up looking silly. Is that this whole push versus pull story is sort of why we're here. Should we, when we're writing these distributed or parallel, concurrent, whatever, computations, should the different, in this case, rows, columns, these grid cells, should they pull information from their neighbors, or should they push changes at them? And if you're just looking at minimizing the amount of contention, pulling is great. It makes contention be read contention, which is relatively cheap to resolve. But push does some slightly more interesting things, I think. So, like the main one in my mind is that when you pull things, when you pull information, you haven't really conducted a transactional update. So if one grid cell says, I'm going to read from each of my neighbors, and if their counts are 4 or more, I'm going to take the appropriate grains of sand from them. The logic there is kind of sound, except when you actually look at the code, it doesn't actually take the grains of sand. It presumes that operator, or sorry, that grid cell will also be run and will appropriately decrement its grains of sand. So this push versus pull thing, outside of synchronous computation, it gets a little wonky. Like if you try to run asynchronously, where in each round of iteration, different people do different amounts of work, doesn't really quite work as well. And the other thing that goes on is that, and I wonder if there's a way we could see this easily. No, I can't think of a good way. Sorry. Is that push is, in some sense, the right model for knowing whether there is more work to do. So in a pull model of computation, every grid cell says at every point in time, I better check. And if you have a million by million grid, that's a massive amount of computation that goes on. I mean, it's largely pointless amount of computation. But like, for example, let's comment out all this stuff here. I need to remember what the shortcut is. We'll put this pile size back on. And let's do 100 grains of sand in a sort of 2 million by 2 million grid, which would take a massive amount of work, like trillions of grid cell investigations, each iteration, just to have them look and basically see, no, there's nothing to do. But the push model, of course, takes, in this case, I guess 32 milliseconds. I don't know if that's good or bad. To be quite clear about where there is actual work to do. So as the sand starts spilling outwards, where is there actually work that needs to get done? And it just turns out that in this case, there's not very much that actually needs to get done. Similarly, with this sort of incremental computation updates, if we ran this to fixed point and then tried to add one more grain of sand somewhere, the amount of work required to move that around is, I actually don't know how big it's going to be. It might take a lot of ultimate time, but these they're going to be very localized, right? So as you drop one bit of grain of sand on, in the worst case, that's going to cause sort of 4 grains to go to nearby piles, and the total number of grains of sand that are going to be moving around are, well, you could have had a very precarious configuration, I suppose. You could have had 3s everywhere, and that'll cause this massive cascade. But I think equally there's an argument that is, on average, as you trickle sand in, not all that much can necessarily happen. That's probably totally wrong, and I feel very silly as a mathematician claiming something like that. But this hopefully gets to the point that the push model of computation actually does work proportional to the work that needs to happen, as opposed to a pull model of computation, which just does all the work and sees what happens. Now, pull model might go a little bit faster when you've decided what work you need to do, but the push model is more effective at identifying what work actually needs to happen. And we'll try to make that point in the future by trying out some different scheduling patterns of how to move all the sand around. So instead of just having everyone go at the same rate, we might try to move stuff, for example, out to the perimeter where it vanishes in a more controlled fashion by essentially scheduling the activations of these things differently. We might learn that makes absolutely no difference whatsoever, but then we'll have learned that. But